Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be going through topics from your online Math 200 class at Ivy Tech for week 13, which talks all about chapter 4, which is describing the relation between two variables. So let's go ahead and start with section 4.1, which goes through scatter diagrams and the idea of correlation. So the objectives in this section are to be able to draw and interpret a scatter diagram, to describe the properties of the linear correlation coefficient, compute and interpret the linear correlation coefficient, determine whether a linear relation exists between two variables, and then explain the difference between correlation and causation. So the first objective is to actually be able to draw and interpret a scatter diagram. So it's first important that we kind of go back. I believe that these topics were first introduced way back in chapter 1, okay? So I want to talk about what the response variable is and then what the explanatory or predictor variable is. So the response variable is the variable whose value can be explained by the predictor or the explanatory variable. So you can use the word explanatory or predictor interchangeably. The response variable can be explained by one of those. So a scatter diagram is just a graph that shows the relationship between two quantitative variables that are measured on the same individual. So each individual is going to be one point on the scatter diagram. The explanatory variable is going to be along the horizontal axis, and the response variable is going to be along the vertical axis. So let's take a look at this example here. We've used this example several times in these videos, but let me go ahead and read the scenario in case you haven't watched the others. So the data shown on the right are based on a study for drilling rock. So the researchers wanted to determine whether the time that it takes to actually drill a distance of 5 feet into the rock increases with the depth at which the drilling begins. So for example, if we begin drilling at the surface, does that take any longer than if we begin drilling 100 feet down? So the depth is going to be the explanatory variable, x, okay, and the time is going to be the response variable, y. So the time that it actually takes to drill can be explained, hopefully anyway, by the depth at which the drilling begins. So we can use the depth in order to explain how long it actually takes to drill 5 feet. So we want to go ahead and use this data to draw a scatter diagram. So you can see a couple of points here. So for example, if the depth begins at 35 feet, then it's going to take 5.88 minutes. If the depth begins all the way at 190 feet, then it's going to take longer. It's going to take 7.9 minutes. And you can see that there is kind of a steady increase here. There are some things that aren't quite linear, but let's take a look at what the scatter diagram looks like. So we have the depth along this horizontal axis, and we have time along the y-axis. So the depth is actually explaining the time, all right? And you'll see each one of these dots represents basically one of the points that we have over here. So 35 feet and 5.88 minutes, that is most likely this dot right here. 50 feet looks like it's about 6 minutes, yeah, 5.99, and so on. 190, I think, is this last dot right here. So we have this little scatter diagram here, and it just allows us to see a visual representation of the relationship between these two variables. So there are different types of relations that we can find in a scatter diagram. So if you have something where the dots are pretty linearly correlated, meaning that they follow this sort of linear shape, and it's increasing, then you have a linear relation. You can also have something where it's decreasing, but the same kind of idea. That's also still a linear relationship. And then down here, you can have something that looks more like this. This looks like a parabola. It looks kind of like the graph of x squared with some transformations. So there's definitely a relationship between these two variables, but it is not a linear one. So we say that there's a nonlinear relationship there. Same thing with this one right here. This pretty clearly has some kind of relationship. It looks cubic, but it's not linear, okay? So you can say that there is a relation, but not a linear one. And then if you look over here, all of these points appear to be kind of random, okay? That indicates that there is actually no relation, okay? So we can have a linear relation, we can have a nonlinear relation, or we can have no relation at all. So we say that two variables that are linearly related are positively associated when above average values of one are associated with above average values of the other. And then the same with below. So below average values of one of the variables is going to be associated with below average values of the other. Another way of saying that is that two variables are positively associated if whenever the value of one increases, the other one also increases. So this is going to look something like this one here where we have this positive slope, okay, it's increasing. So those two are positively associated. Negatively associated is the one where we had our decreasing slope or negative slope. So the two variables that are linear related are negatively associated if above average values of one variable are associated with below average values of the other. Or we could say that as one increases, the other one decreases. So we have kind of this negative relationship here. So the variables can either be negatively or positively associated if they're linearly associated at all. Okay, now objective 2 is to be able to describe the properties of what is called the linear correlation coefficient. So the linear correlation coefficient, it can also be called the Pearson product moment correlation coefficient. It's just a measure of strength and direction of the linear relation between the two quantitative variables. So the Greek letter rho actually represents the population correlation coefficient, and R is what we're typically going to see because that represents the sample correlation coefficient. We're only going to look at the sample one in this section. So we have this formula here, okay? So our sample linear correlation coefficient is found by taking xi minus x bar, where x bar is the sample mean of the explanatory variable, divided by s of x, which is the sample standard deviation of the explanatory variable, and then multiplying that by yi minus y bar, where y bar is the sample mean of the response, divided by s of y, which is the sample standard deviation of our response variable y. So we take those, we multiply, and we sum them all up for all of our observations from I all the way to n, and then we divide that entire thing by n minus 1, where n is the number of individuals in the sample. So this can be fairly time consuming to do by hand. StatCrunch will do it for you very easily. So I would recommend to make sure, I believe since this semester you're not allowed to StatCrunch on the exams or quizzes, that you do know how to do these either in your graphing utility or how to set up a table for it, which is not too difficult. We'll take a look at that so that you do know how to do it on an exam, for instance. But for the homework, so that it doesn't take you too long to do, I would recommend doing a couple of them by hand and then probably relying a little on StatCrunch to help you get this. So there are several properties of the linear correlation coefficient. The first property is that it always has to be between -1 and 1, inclusive. So -1 is less than or equal to r, which is less than or equal to 1. Now, if r is equal to +1, then that means that you have a perfect positive linear relation, okay? This is very, very rare to actually see with real data. If r is -1, then a perfect negative linear relation exists. If r is closer to +1, then that's stronger evidence of some positive association between the two variables. And if r is closer to -1, then that indicates that there's kind of not kind of, but there is stronger evidence of a negative association between the two variables. Now, if r is close to 0, then that would indicate that there is not really any evidence to suggest that there is a linear relation between the two variables, okay? Now, it's important to stress that that just shows us that there's no evidence of a linear relation, but there could be some other kind of relation. So you could have r close to 0, but you could have some kind of quadratic relation, like an x squared type of relation or something else entirely. So it's important to say that it's not that there's no correlation, it's that there's no linear correlation or relation. So the linear correlation coefficient is a unitless measure of association. So the unit of measure for x and y actually plays absolutely no role in interpreting r. and the correlation coefficient is not resistant. So if an observation that doesn't actually follow the overall pattern of the data, then it could potentially affect the value of the linear correlation coefficient fairly significantly, depending on how different that observation might be. So let's take a look at some examples here. So this would be an example of a perfect positive linear relation where r is equal to 1. Okay, these are all in exactly just one straight line. And then if you look over here, this is an example of r equals -1. Okay, this is a perfect linear relation, but it's negative, okay, because it's decreasing. If you look at this, this is very strong, this linear relation. All these dots are pretty closely aligned and they follow a very strong line here. So that would be an R of about 0.9. You can look at this one, it kind of shows same sort of thing. We have something that's linear and not perfect, but this one, our data is more spread out. Okay, we have more variability in our points. So this would be an R of about 0.4, just to give you an idea. This one would be a strong negative linear relation, so it looks just like this one over here, very, very close together, but negative, so it's about -0.9. And then this one, it obviously has some kind of negative relation, but the points are a little more spread out, so it's -0.4. This one here appears to be totally random and not have any shape, so that would give an R that's very close to 0. And then this one, it would also give a value of r that's close to 0, but if we actually look at it, it does have a relation, but it's not a linear relation. So let's actually go ahead and compute and interpret the linear correlation coefficient. So let's look back at our drilling data. So we have our drilling depth and then our time to drill. So what's done here is this is organized in a table, and this is pretty much what you have to do if you have to do this by hand. So if it is required for you to do this by hand, if you don't have some kind of handheld utility that will do it for you, then you're probably going to want to set up a table like this, where you have your x's and your y's, and at the very least, I would use your graphing calculator to go ahead and calculate x bar, y bar, s sub x, and s sub y, so your sample standard deviations and your means. So I would definitely do those using some kind of graphing utility. All right, so you're going to have a mean, sample standard deviation, And then what you're going to do is for each pairing, you're going to take your xi, meaning your observation here, your 35. You're going to subtract the mean, so you're going to subtract the 126.25. And then you're going to divide by the sample standard deviation of 52.22874. And for this particular one, you get -1.74712. So that's taking 35 minus my mean divided by my standard deviation. Now, again, if you are doing this by hand and you're doing it in your calculator, you will want to put parentheses around your numerator. And then we're going to do the same thing going across, okay? So through this row, we're going to do the same thing for our y's. So we're going to do our 5.88. We're going to subtract our y bar of our 6.985833. 780,774, and we get -1.41633. So that's this piece right here. And then we have to multiply these two numbers. Okay, so we multiply this value that we had gotten, this value that we had gotten, and we have 2.474501. Okay, so this, for example, is our first one. And we're going to do this all the way down. You can get negative values in this if you have a negative for one and a positive value for another. And then once you have all of these values, you go ahead and you add them all up. So you would just take your calculator, or again, if your graphing utility will calculate R for you, I would highly recommend that you do that because this can be fairly time consuming if you have a lot of observations. But if you add all of these up, you should get 8.501037. So that's your numerator, and then all you have to do is divide by n minus 1. So if you look back, we actually have 12 pairs, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and this is the number of actual pairs. So it's not that we have 12 x's, 12 y's for a total of 24, it's 12 total. So we take our 8.501037 and we divide by 11 because we have 12 minus 1 or 11 degrees of freedom. And this is just the same as finding degrees of freedom for our TD distribution. So if you go ahead and divide these, you get 0.773. So if you want to actually determine whether a linear relation exists, you have to do a couple of things. So step one is to determine the absolute value of the correlation coefficient. So that would be using the process that we just used. Finding the actual correlation coefficient, determining the absolute value would be fairly simple from there. Step two is to go ahead and find the critical value from a table 2, okay, and that's in your appendix. And then if the absolute value of the correlation coefficient is greater than the critical value, then we say that a linear relation exists between the two variables. Otherwise, no linear relation exists. So if we want to determine whether a linear relation actually exists between drilling time and depth, then if we go ahead and take a look at this here, we have 0.773, that was our correlation that we had found, and we have n equals 12, so we're going to look over at 12 observations, and we find the critical value to be 0.576. So that means that with 12 observations, if you have a correlation coefficient of at least 0.576, then you are going to have a linear relation. So if we take a look at this, 0.773 is definitely greater than 0.576, so we can say that there is a positive linear relation between time and depth. And the reason that we can say that it's positive is because the correlation coefficient was positive. It was 0.773. If the correlation coefficient had been negative, then we would have said or would have concluded that there is a negative linear relation. So you're always looking up absolute value on this table, and then the actual sign that's on your correlation coefficient determines whether there's a positive or a negative linear relation. Now, the other way that we should know this is the very first thing that we did is we looked at a scatter diagram of this data, and it pretty clearly showed that we have some kind of positive relationship between the two, okay? And it did look linear, so we should be expecting there to be some kind of positive linear relation. Okay, now objective 5 is to be able to explain the difference between correlation and causation. So according to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940, which is a very high correlation coefficient. So what we want to know is if this means that a higher percentage of females with bachelor's degrees causes a higher percentage of births to unmarried mothers. So obviously this is not going to be the case, okay? So the correlation exists only because both percentages have been increasing since the year 1990. So it is that relationship, the one to time, that actually causes the high correlation. So in general, time series data, meaning data that's collected over time, might have high correlations just because each variable is moving in a specific direction. So we can use one to predict the other because of the fact that they're both moving in the same direction over time, but it doesn't mean that they're actually correlated with one another. Or it doesn't mean that they're actually causing one another. So they're highly correlated, but there's no causal relationships there. So when data is observational, so when you're looking at observational studies, you could not claim a causal relationship exists between two variables. So you can say that they're correlated, but we cannot actually say that one causes the other. So you can only claim causality when the data are collected through some kind of designed experiment where you're able to control for all of the factors. Otherwise, there are too many lurking variables and issues with confounding that cause us to see things that are highly correlated but actually have no causal relationship. So another way that two variables can be related, even though they're not in a causal relation, is through some kind of lurking variable. So a lurking variable is one that's related to both the explanatory and the response variables. So for example, ice cream scales and crime rates actually do have a really high correlation if you look at them. So we want to know if this means that local governments should shut down all ice cream shops because they're causing crime rates. And this is certainly not the case. If you think about it, the lurking variable is going to be temperature. So as it gets warmer out, ice cream sales and crime rates both increase because you have more people out. So they're definitely correlated, but one does not cause the other. And the lurking variable there is temperature. Okay, Now in section 4.2, we're talking about least squares regression, okay? So we want to actually find the least squares regression line and then use the line to make predictions, interpret the slope and the y-intercept when possible. So let's take a look at this data here. So we have sample data, it doesn't have necessarily any kind of story behind it, okay, but we have our values for x and we have our values for y. So we want to find a linear relation that relates x, which is our explanatory variable, with y, which is our response, by selecting 2 points and finding an equation of the line containing the points. So you should be pretty familiar with this, okay, from previous math classes. But if we use points 2 and 5.7, so that's this pairing right here, and the 6 and the 1.9, what we're going to do is we're going to calculate slope using change in y over change in x, and we get negative 0.95. And then we also are going ahead and plugging in the 5.7 and the 2 in for x1 and y1 into our point slope form. And we're solving this to get y equals negative 0.95x plus 7.6. So that's the actual equation of the line that we found. And it looks something like this. So we have our scatter diagram here, we have all of our points, and then we have our actual line here. All right, so this is the line that we just created. It goes directly through, it should go directly to through the 2 and the 5.7 and the 6 and the 1.9. So if we look, it actually should go directly through this one and this one as well. So if we want to use the equation to predict y if x is 3, that means we would just plug in a 3 for x and solve, and we'd get 4.75. So that means that over here at 3, we would predict our x value to be 4.75. Now, this is a line, okay, and it fits our data, but it's not the best fit line. So what we're actually going to find is something called the least squares regression line. And this is going to be a better line that can be used to make predictions. So if we look at the difference between an observed value of y and a predicted value of y, that's going to be called the error or the residual. So if we take a look here, we have an actual value for y and we have a predicted value for y. So if we take what we observed and we subtract the predicted, we're going to be left with some kind of residual between these two. Okay, so for example, for the last one, we actually observed at 3 a value of 5.2, but we predicted 4.75. So we have a residual of 0.45. Now, what the least squares regression line actually does is it minimizes the sum of the squared errors or squared residuals. So the line that minimizes the sum of the squared vertical distance between the observed values of y and those predicted by the line, which is a y hat, okay, is going to be represented as such. We're minimizing the sum of the squared residuals. So we're going to take all of the residuals and square them, and that is going to be minimized by our least squares regression line. So if we take a look at the general formula for your least squares regression line, you have y hat equals b1 times x plus b naught, okay? b1 needs to be found first. You take your r, which is your linear correlation coefficient, and you multiply that by the standard deviation for y divided by the standard deviation for x. And that gives you the slope of the least squares regression line. And then once you have that, you can calculate b naught by doing y bar, which is the mean for your y values, and subtracting b1 times x bar. So one kind of note here is that x bar is the sample mean, s of x is a sample standard deviation, y bar is a sample mean, and s of y is a sample standard deviation for the response variable for y, explanatory variable for x. So you've already seen that notation. Hopefully you're very familiar with it at this point. So if we look at our drilling data, we have the same data here, and we can go ahead and calculate this. The actual calculations are not shown here. We can use StatCrunch in order to do this fairly easily, okay? But if you go all the way back to where we had that original table where we calculated our linear correlation coefficient, we actually have all of these pieces that we need. We have the standard deviation for y, standard deviation for x, we have y bar, and we have x bar, and we have r. So if we actually went back to that, we could calculate all of these values. And what we would get is we'd get a slope of 0.0116 times x. or sorry, the slope is just the value here, and then it's multiplied by x. And then we'd have a y-intercept of 5.5273. And then if we want to predict for maybe 130 feet for drilling, we would actually plug in 130 in for x, and we'd multiply by our slope and then add our y-intercept, and we'd get 7.035. So the observed drilling time is 6.93 seconds, and we predicted it to be 7.035. So the drilling time of 6.93 is a little bit below average. So if we take a look at this data, we have, it's kind of hard to see these light blue dots. I apologize for that. But that was our original scatter diagram of this data. And then you can see that we've overlaid this least squares regression line here. And that's the solid line right here. So this is the line that we're actually using to predict how time changes as the depth of drilling changes. Now, if we want to interpret the slope and the y-intercept, we have to think a little bit about the actual scenario. So we know that the slope of the line is 0.116. So that means in this case, every additional foot that we add, we're going to add this many minutes. Okay, so for every additional 5 feet, we're going to be increasing by 0.0116 minutes on average. And then if we want to interpret the y-intercept, this one, we need to make sure that a value of 0 is reasonable. And then we want to make sure that values near 0 exist in the actual data. Otherwise, we might be going kind of too far out of the realm of where we should be predicting. So a value of 0 is reasonable in the drilling data because that's just going to indicate that we're starting drilling at the beginning of the surface of the Earth. Okay. Now the smallest observation is x equals 35 feet. So it's pretty close to 0. It's reasonably close. So the interpretation seems pretty reasonable. So that means that the time to drill 5 feet when beginning drilling at the Earth's surface was 5.5273 minutes. So it makes sense for us to write this interpretation because 0 is a reasonable value for the explanatory variable and observations near to 0 actually do exist in the data. But if that was not the case for either of these questions, then we would not want to actually interpret the y-intercept. Now, one kind of word of caution here is that if the least squares regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, then the researcher is going to be working outside of the scope of the model. And we never want to use a least squares regression line to make predictions that are outside the scope of the model because we can't be very sure that the linear relation continues to exist. So we only know that it exists on the points for which we've built it. We can go a little bit outside of there, but not too far. Now, there is not really a rule of thumb that I know of, or that is explained in the textbook anyway, that says that it's much larger or much smaller. So just use your best judgment when you're answering those types of questions. It should normally be fairly obvious. Okay, now section 4.3 is about the coefficient of determination. So if you want to compute and interpret the coefficient of determination, that's your R squared value. And what it does is it actually measures the proportion of the total variation in the response variable that is explained by the least squares regression line. Now, it always has to be a value between 0 and 1. It can be 0, it can be 1. R squared is going to equal 0 if the line explains absolutely nothing. Okay, so the line has no explanatory value. R squared equals 1 means that the line explains 100% of the variation in the response variable. So it does a perfect job of explaining the variation in response. So if we take a look back at our drilling data, here was our initial scatter plot. We had our sample statistics, we had our mean and our standard deviations, we had our correlation, and we created our regression equation. Time was equal to 5.53 plus 0.0116 times the depth. So let's suppose we were asked to predict the time to drill an additional 5 feet, but we didn't know the current depth of the drill. So our best guess would be the average time, which would just be 6.99 minutes. But now we can use our equation to actually answer that a little bit better. So let's say that we're asked to predict how long it's going to take to drill an additional 5 feet if we're at 160 feet. So what we would do is we'd actually plug in 160 into our equation and we get 7.39 minutes. So our guess increased from 6.99 to 7.39 based on the knowledge that the drill depth is positively associated with drill time. So the difference between the observed value of the response variable and the mean value of the response variable is called the total deviation. And basically it's just equal to y minus y bar. Now, the explained deviation is the difference between what was predicted and the mean value of the response, and that's going to be your explained deviation, y hat minus y bar. And then we have unexplained deviation, which is going to be just y minus y hat. And that's the difference between the observed value and the predicted value. And together, what we do is we take our unexplained deviation, that's our y minus our y hat, and our explained deviation, that's our y hat minus our y bar, which is shown right here, and that gives us our total deviation. So, in order to determine r squared for the linear regression model, we simply square the value for the linear correlation coefficient. Now, one word of caution is that squaring the linear correlation coefficient to obtain the coefficient of determination only works for the least squares regression model. So in general, the method does not work. It only works for the least squares regression model. So let's find and interpret the the coefficient of determination for our drilling data. So we know that R was 0.773. So all we have to do is square that value. It's really, really easy once you know your linear correlation coefficient. So if we square that, we get 0.5975, which we want to change to a percentage in order to interpret it. So that's going to be 59.75%. So that means that 59.75% of the variability that exists in drilling time is explained by our least squares regression line. Okay, let's take a look at this right here. So let's draw a scatter diagram for each of these data sets A, B, and C. And then it tells us that for each data set, the variance of y is 17.49. So if we take a look at this one, we have data set A here. We have all of our values here. This one is very, very close to the actual line. So this one would maybe be 99.99% of the variability in y is explained by the least squares regression line. This one looks pretty good. Okay, our dots are pretty close. We have some that are right on there. This one looks like an r squared value maybe closer to 95. Okay, so it's 94.7% of the variability in y is explained by the least squares regression line. And then for data set C, this one does not really look very good. We have values that are quite far from our regression line. So only 9.4% of the variability in y is explained by our least squares regression line there. Okay, so let's take a look at a couple of kind of extra examples. So let's determine here the type of correlation that exists between two variables. So if you take a look at this one right here, hopefully this looks like some kind of linear correlation to you. And if you look, this is definitely decreasing. So it has a negative slope. So this one has a negative linear correlation. If we take a look at this one right here, this definitely has some kind of correlation, but it's not positive linear, it's not negative linear. So this one's a nonlinear correlation. Now, if we take a look at this here, we've created a least squares regression line for temperature, which is x, and number of ice cream cones that are sold per hour, which is our y, and we want to predict the number of ice cream cones sold per hour when the temperature is 88 degrees. So all we have to do in this case is just take 88 and plug it in for x. So I want you to go ahead and do that in your calculator. So if you plug 88 in for x, you're going to take 88 times your 0.383, and then you're going to subtract your 17.694, and you get 16. So when the temperature is 88 degrees outside, we expect to sell about 16 ice cream cones per hour. Now here, we have the data for temperature x and the number of ice cream cones sold per hour y, and we want to know if it'd be reasonable to use the least squares regression line to predict the number of ice cream sold when it's 50 degrees. And for this one, we're going to say false, okay, because 50 degrees is fairly far from any of the other observations that we have. And if we actually plug 50 in, let's see, I'm not sure exactly what we're going to get. Let's go ahead and try it. So let me grab my calculator. I'm going to plug 50 in. So I have 50 times 0.383, and then I subtract the 17.694. Let's see, I got 1.456. That's fairly small. So 50 degrees might not be so reasonable, okay, because it's fairly far from our original value of x, which was 65. That one is a little hard to kind of predict. Definitely you wouldn't want to do anything that would be 40 or 30 degrees because that is quite far. And what's actually going to happen when you predict them is you'll probably get some negative values here, which is not going to make any sense because you can't sell a negative number of ice cream cones. And then let's take a look at this. Let's analyze the residual plot and identify which, if any, of the conditions for an adequate linear model are not met. So any issues that might exist. So if we look at this, we have values that are fairly consistent. And then towards the end, we have these values that are very far from our baseline right here. So it does not actually look like there is a constant error variance. So for this one, that is going to be the issue, is that the errors vary by a significantly larger amount at the end. If we take a look at this, we have definitely some kind of shape going on. So this is going to be a matter of patterned residuals, meaning that our residuals are following some kind of trend, okay, which we want them to just look random.